All right. So it's the strong survive in this class. So we will. You should have everything you need. That connects assignment that's due at the end of the day, Wednesday. We covered all that stuff last week. I think the last stuff we covered was on Wednesday. We did match pairs. We'll look at how we do match pairs in Excel today. That'll be the last question that you need for this 4th Excel assignment. Once again, that's not due until next Friday. But I'm also going to put up this afternoon one more Connect, one more Excel assignment that'll also be due that Friday. Drop the lowest score. So if you've done the first 4 of either one, and you're okay with what you done there, you don't have to do the 5th ones, right? Those would be the ones that get dropped. Other than that, I'll also get some practice exams up. We're a little bit, further away from the exam. I'll have to start looking at those necessarily right now, but I'll get them up there. You'll kind of see those on campus. So you'll have those as you begin to think about the final here. Okay. Questions for me before we jump into material here too? Okay. So kind of left off, right? We had this population HT blank file we started with. We worked through an example where we looked at the difference in, well, I think if we go all the way back. Oh, did I not save this one? I'll have to redo this. You don't need that for the homework, so it's not a big deal. But we did the difference in sample proportions here between kind of our, proportion of our males and females that were white in each sample. We also did the differences in BMI between males and females with this data. So this was sample means where we only had sample variances. Today, we're going to look at how we do matched pairs. So matched pairs was where we had this mean difference variable. And we said it kind of goes back to looking at one population mean example, just notating it a little bit differently, which is that we're not looking at the mean of one variable. We're looking at the mean of this difference variable we created using 2 other variables. Right? So we've got our confidence interval and our hypothesis testing equation. Okay. So we're going to go up here. Now I've got all this data, and it's got per county, kind of male suicide, female suicide numbers. Okay. I'm going to look at the average difference per county between male and female suicides. Now, I'm going to delete this column real quick just to show you how you can kind of create this difference variable pretty quickly. So all I'm going to do is take my male suicides minus my female suicides in this county, hit enter. Now, if I go back to this cell and I get this kind of thick black plus sign here, if I double left click, it does that for every single observation here. Okay. So I now have this difference variable. That's what I want to find the mean, the variance, and the sample size of. Okay. Well, hopefully at this point, that's not too tough for us, right? The average function of this difference variable, right, would give us our sample mean. So Control Shift, hit the down arrow, Command Shift on the Mac, hit enter. We'll send this all the way. Whoops, enter, sends us all the way back up. Sample variance, var.s. Select that very first observation. Control Shift, hit the down arrow, hit enter to close the parenthesis. And then last but not least, we need that sample size. Actually, it's last and probably is least, but we'll take the entire column for this difference variable. Now we've got our sample mean using the average function, sample variance using the var.s, sample size using that count function. Right? So hopefully kind of getting familiar, right? Just finding those sample means, sample variances, sample sizes. From there, we've got everything we need except for that number of standard deviations the way we need to go, or that t-value. So what we're going to be doing there is, this is kind of a reminder, we want to know, okay, what is the number of standard deviations the way we need to go in each direction to get there to be an alpha total outside my confidence interval? And if I've got 2 sides, my confidence interval, alpha over 2 on each side. So I know the area I want in the tail. I've got these 3 benchmark alphas. If I know the area in the tail and I want to find the t-value, remember what equation we said we could use there? First of all, yeah, t dot something, right? T dot I and V, right? Anytime, oh, sorry. I hit something on my, there we go. I can't type today. There we go. T dot I and V, right? Anytime we know we want the area we want in the tail, and we want to find that corresponding t-value, that's the inverse process. So we use t dot I and v, and that area I want in the tail is alpha divided by 2. Now, with a student t distribution, I have to tell it one more thing, right? Which is my degrees of freedom. We said with these matched pairs or these mean difference variables, my degrees of freedom simply goes back to what? Do we remember? So with one population examples, the degrees of freedom was simply our sample size, yeah, -1. Okay. So I've now got, one of my p-values I need, 90% confidence level. But if I want to get the next 2 confidence levels pretty quickly, and I copy this down, I want alpha to change, right? But my sample size, my degrees of freedom should be the same thing, okay? So if I go in here, I should freeze that cell where I've got my sample size, okay? Any questions on that before we keep moving here? Okay, shouldn't be too bad. I've kind of done this already. What did I forget to do? Yeah, right. We said that positive and negative are already built into my confidence interval lower upper bound equations. So one easy way to fix that is just go in, take that absolute value, right? Now, when I copy this down, I should get the t-values I need for these 3 levels of confidence. Okay. Now, just to kind of make this point, make this connection. So especially once we get to hypothesis testing with linear regression, which is the next topic I'll introduce today, once we're done with Excel, we kind of sometimes move back and forth in between significance and confidence levels. So my significance levels are like these alpha values I'm comparing to, but in percentage form. So my alpha is of 0.1, 0.05, 0.01. That's 10, 5, and 1% significance levels, which correspond to the 90. Okay, what did I do there? Hold on. I bumped something. 90, 95, and 99% confidence levels. Right? So we can kind of go back and forth. If I can reject with 90 and 95% confidence, I'm rejecting at the 10, 5% significance levels. So from here to my lower and upper bound, it's just a matter of using Excel to be my calculator. Right, so I start this equal sign. I say, okay, look, take my mean difference, then subtract from that the number of standard deviations I want to go, which I got from my t distribution here. Oh, why did I do that here? Minus, there we go, the t value. Multiply that by the square root of, do I keep bumping something that erased it? Here we go. So mean difference minus that t value times the square root of my sample variance divided by my sample size, right? So all I'm doing is using Excel to be my calculator. I've got the 4 pieces of information I need. Instead of typing into a calculator, I'm just clicking on the cells where those numbers are at, okay? So from there, if I want to copy this down, what's the only thing that should change at different levels of confidence? Alpha, which will then change my corresponding t-value, right? So that's the only thing I want to update when I copy this down. So everything else, I'm going to use that F4 key or FN F4, or if you don't have an FN key on your Mac, Command T. And I'm going to freeze everything except for that cell reference for my t-value, okay? Now, if I want to do my upper bound, it's going to be the exact same equation except for what? I add that margin of error instead of subtract it, right? So I'm just going to select this entire, double click on here. I'm going to copy it, hit enter to get out of the cell, paste it, get the same value. Oh yeah, that's because instead of subtracting my margin of error, I want to be adding it, right? Now, if I do it this way, I can copy this down, and I should be able to get my 3 upper and lower bounds relatively quickly. But really, you just have to type it in one time, right? Copy, paste, your lower bound equation to your upper bound, change the negative, subtracting that margin of error, change that to a positive. Then if you freeze those cells correctly, you get whatever, I got 3 here. I could get 10 different levels of confidence if I really wanted to. Any questions on that before we keep moving here? Shouldn't be too bad. I mean, we've kind of done a lot of confidence intervals building up to this point. So the next thing we're going to do is some hypothesis testing, right? So what I'm going to assume to start out, and actually, I'm going to change these values. Come back here in a second. I'm going to use this assumed true difference of 0. So I'm just going to put a 0 down there in that cell. So we're going to want to test for whether or not this average difference in male-female suicides is greater than or equal to 0. So assume the opposite is true for our null, which is that's less than or equal to 0. Right? So I've got what type of tail test here? I got a greater than sign of my alternative hypothesis, so right tail test. Right? Now before I go and start doing this hypothesis test, doing both the p-value and critical value approach, try to make this connection between confidence intervals and hypothesis testing. Here's my confidence intervals. My confidence intervals tell me these are the with 90, 95, 99% confidence. Here are the range of possible values that could be the true difference. So if I'm assuming that the true difference is 0 or something below that, what should be my rejection decision based off of my confidence intervals? If I'm assuming, say, the difference is equal to 0, I look at that confidence interval, what would I say? Is 0 in that range? No. So if I with 99% confidence am saying the true difference is somewhere in this range of values, 0 is not in that range, I should be rejecting that assumed true value of 0 then, right? Any value outside of this range that I assume that the difference is equal to, I should be rejecting, right? If I have a value that's within that confidence interval, well, I should be failing to reject, right? So we hopefully already know the outcome, but we'll walk through the steps, right? So the first step is, well, I need my test statistic, right? It doesn't matter if I want the critical value or p-value approach, I need this test statistic. There's no nice built-in formula in Excel. This is just something we have to use Excel to be our calculator. So my numerator, I'm going to take that mean difference and then going to subtract my assumed true difference of 0. Okay. I'm then going to divide by the square root of my sample variance divided by my sample size. Right? I'm just looking at that formula and I'm kind of getting it entered in to Excel, right? Just using Excel to be my calculator. Okay. Now, if I hit enter here, right, I get about 39. So if I want to find the p-value for a right-tailed test, it would be the area to the right of my test statistic. If my test statistic is 39, what's my p-value going to be really close to? We start to get test statistics or the z or t values that are above 3 or 4. The area to the right of that is essentially 0. So the area to the right of 39 is going to be really close to 0, right? So if I'm making my rejection decisions based off of is the p-value less than alpha, well, if I get a p-value of 0, it can pretty much reject at any level. Right? It's going to be less than any of my alphas. Now we can actually work through if we had a more interesting test statistic, how would we find the p-value? So I now know that t-value and I want to find the corresponding area in the tail. So now I'm using the t dot dist. Right? Here's my t-value, comma, well, what's my degrees of freedom? Just my sample size minus 1. And then comma 1, we always make it cumulative, right? We're always kind of getting that cumulative probability. The 0 option here doesn't really do anything. So I'm going to hit enter here. There's going to be one problem, right? I get that the p-value is 1. Well, before I said it was pretty much 0. What did I do wrong here?
The area to the left.
Yeah, the norm.s.dist and the t.dist functions always give me the area to the left of whatever z or t value I tell it. So if I want the area to the right, I still need to do 1 minus that, right? So if I know the area to the left was almost 1 minus that, I get a p-value of basically 0, right? It's so small, Excel doesn't even register as anything except for 0. Any questions on that before we keep moving? Okay, so I can do my rejection decision with the p-value approach if I wanted to. I can use that if function and say, look, if my p-value is less than alpha, well, if that holds, comma, put the word reject into this cell, right? Because I should be rejecting. If that doesn't hold, comma, put the word fail to reject. And I can make this rejection decision at 3 levels relatively quickly because all I'm doing is comparing my p-value to different alpha values. So if I copy this down, my alpha would update. I don't want my p-value to update, so I need to do what? Go in and freeze that reference, right? Now, when I copy this down, I'm still using that same p-value and just comparing it to different alphas. Okay. So hopefully, if what we said, if we did everything correct, we should get rejection at every level, right? If the p-value is pretty much 0, we should be rejecting at every single level. Okay. Now, let's instead say I wanted to use critical value approach. Right? So I've got this right-tailed test. And I want to know, well, what's the cutoff t-value that's going to give me alpha total in my right tail for a right-tailed test? So what has to be true about my critical values for a right-tailed test? Yeah, our z and our t distributions are all centered around 0. So right-tailed test, my values will be positive. Left-tailed test, critical values would be negative. Two-tailed test, I'm going to have a critical value on each side, same value, one positive, one negative. So we'll just start out with the alpha of 0.1. Right? How can I find that critical value, that cutoff t-value that gives me 0.1 in the upper right tail? Well, once again, if I know the area in the tail, I can use that t.inv. I want alpha in my tail, comma, degrees of freedom is sample size minus 1. Now, if I copy this down, what don't I want to change? I want to find the critical value at different levels of confidence or different levels of alpha. I want alpha to change, right? I need to find the different t values corresponding to different alphas. But my degrees of freedom, that sample size minus 1, that's always going to be the same value. I'm referencing the same cell there, right? So I'll freeze that cell reference. Now, I also have one more problem here. If I hit enter, what's going to be an issue? What's wrong with my critical value? Yeah, it's negative, right? So why is it negative? Kind of like what we do with the standard normal by hand. Our t.inv and norm.s.inv, the area or the probability you tell it is the area in the left tail. Now that's okay for if you wanted to. Well, if I've got negative 1.28 and the area to the left is 0.1, well, that just means the area to the right of positive 1.28 would be 0.1, right? Because it's symmetric around 0. So I could just remember like, oh yeah, I can just tell that t.inv alpha, and then for a right-tailed test, I just have to make it positive, right? So I could use the absolute value. Or if I know the area to the right of this value is 0.1, what would be the area to the left? 0.9, right? Or 1 minus alpha, right? Whatever my alpha value is, whatever the area I want in the right tail, the area to the left will always be 1 minus that. So 2 different ways of doing that. You could use the absolute value if you just remember, oh yeah, tell that t.inv alpha, and then if it's a right-tailed test, I have to make it positive. That's fine as well. Right? So now we've got our critical value at all 3 levels. I just copy that down as long as we froze that degrees of freedom correctly. Okay. From here, how do I make my rejection decision? Well, here it gets a little tricky, but I'll show you a way that works regardless of the type of test. So if my test statistic of, here, I think this is what, 1.28 or 29. My test statistic is very clearly in that rejection region, right? But if I don't have the visual and I want to do this mathematically or I want to do this in Excel, what I'm really saying is this test statistic for a right-tailed test, is it greater than my critical value? The only problem is for a left-tailed test, my critical value would be like negative 1.28. And if I found something out here, well, now if I find a test statistic out here, I only reject if it's less than, right? because now larger negative values are actually smaller. So the way that we say this, and I always say it in words, is we always reject if the test statistic is more extreme than my critical value. What I'm really saying is there, I only want to be comparing magnitudes, right? So if the absolute value of my test statistic is ever greater than the absolute value of my critical value, that kind of deals with this issue of like larger negative values, then that's what I'm going to be rejecting. So I could say, okay, look, if the absolute value of this critical value is ever less than the absolute value of my test statistic, that means this threshold cutoff number of standard deviations I set, my sample data was way past that. So I want to be rejecting. So comma, put the word reject, and then comma, if that's not true, put the word fail to reject. Okay. So this is another way, this is the critical value approach where we can make our rejection. Hopefully, it lines up with exactly what we did with the p-value approach if we've done everything correctly. Okay. Any questions on this? Keep moving here. Want to go back to a different cell or any? Okay. A little bit quicker with you guys in the last section. So let's copy this down. Oh, what did I do wrong? Why am I not getting reject down here? When I copy this down at different levels of confidence, my critical values will change, but that test statistic should still be using the same value, right? Well, I did not freeze that. So when I copied it down, wrong cell. Now when I when I copy it down, I'm using blank values, right? So I'm going to go to that test statistic, reference, freeze it. Hopefully now, there we go. Makes a little more sense, right? Any questions on anything? You want to see something again? Follow along, okay? Okay. So I've got my rejection decisions, right? I've got one other way I could kind of find this p-value, right? So I didn't show you the shortcut yet. We had a shortcut when we had the difference in sample means and we had sample variances. We said we could use this t-dot test option, right? So what we're going to do with this t-dot test option is it says kind of select array 1 and array 2. Well, this is basically your two variables, right? Well, here we only had this one variable, which was the difference variable, but we created it. So if I go over, how did I create that difference variable? Well, the first thing I did was take this male suicide variable. So select that. I'll kind of scroll up to show you. So that was my first array, comma, or my first variable. The next variable was this female suicides variable. So I'll control shift, command shift on a Mac, hit the down arrow, puts that cell reference in there, just so we can see it. I'll scroll back up to the top. So I've got my first variable, my second variable, comma, how many tailed tests did I have here? Well, we had a one-tailed test. And then comma, what type of test do I have for this t-dot test option? Well, I said last class, which of these numbers will we never use? 2. Right? I said nobody should be using 2. We're not doing anything with that in this class. We either have a type 3, right, which is 2 sample means with different variances. That's what we did last class. Or we have a matched pairs example, right? I've got the same counties that I'm looking for the difference between male and female suicides, right? So I've got one population, or this matched pairs example, which it reminds me is type 1. Okay, so I'll make this easy, right? Well, I'll come back to this in just a second. So if I hit enter here, what this will do is it takes that male and female suicide variable, finds the difference between those two, calculates the mean of that difference variable, the variance of that difference variable, the sample size, throws them all into the test statistic equation, looks it up in the table, finds the area in the tail. That's your p-value. It's a 2-tailed test. The area in your tail, you have 2 tails, so you multiply it by 2. It does all that behind the scenes for you. So it essentially takes the original data, does all the work, and spits us out at us the p-value. Now, here, if we break it down step by step, notice these are a little bit inconsistent, but 5.9 to the negative 232, that means 231 zeros, and then a 5. This is basically 0, right? This T-dot test option just rounds, like it actually rounds out to some 100th decimal, where the other one kind of keeps things out further. And so we'll get a little bit of an inconsistency if we have really, really small p-values like this. But I'll show you in a second, if we have different, a little bit higher p-values, these two will look no different out to like the 100th decimal, right? So a real nice shortcut, right? So what I want you to ever know how to do it, breaking it down step by step. So on the homework, I will ask you, essentially, I'll give you a roadmap. This sample proportion, this is problem 1 in the homework on Excel, right? It's going to be very similar. Now, I might do like, switch up, is it a left or right, or a two-tailed test, right? But it's going to be a difference in sample proportion example. This is going to give you like the basic scaffolding for what you want to do. Problem 2 is going to be very similar to when we had 2 sample means, sample variances. We're looking for, differences between 2 group sample means. There, when we did the T-dot test, we said we used, oops, that's not what I wanted. Where is that? Here it is. It was a type 3, right? So right now I'm telling you, if you're listening, problem 2 on the Excel homework, you're using a type 3 when you use that T-dot test option, right? Now I'm going to have you do it first, breaking it down step by step, and then use that shortcut. And then on problem 3, I'm going to do a similar thing. I might ask you to kind of break it down step by step and then use that shortcut T-dot test. And here for the question 3 on the homework, you'd have this type 1, right? It's a matched pairs example. So these are the 3 problems that'll be roadmaps for how you do those 3 problems on that board of Excel. Now, we've already done 2 of them last week, so you could have already started working on those, but here's kind of the last one that you would need. Now, the reason why I have you do it step by step and then use this shortcut, like, not just for the sake of like giving you extra homework, because let's say, okay, I can very clearly reject this assumed true difference of 0. Like based off the sample evidence, I found an average difference of like 44, right? So maybe instead, I can very easily say that the difference between male and female suicides on average per county is greater than 0. Can I say that it's greater than 40? Or can I reject that that difference is less than or equal to 40? Well, if I've got this set up where I was referencing this assumed true difference cell here, before it was 0, so could have ignored it if I really wanted to. Now I'm going to change it to 40, okay? So if I hit enter here, before we do that, if I look at these confidence intervals, what levels should I be able to reject that assumed true difference of 40 at? We said before, when we assumed the difference was 0, we knew we were going to reject. Why? It wasn't anywhere close to being in our confidence interval, right? It couldn't be one of the possible true differences. So if I'm using an assumed true difference of 40, will I be rejecting or failing to reject that? If I look at these confidence intervals, is 40 in any of them? Well, this one stopped at 42, so 40 would be outside of my interval. 42.4, 40 is outside of the interval. 41.7, 40 is outside the interval. So if the value I've assumed that the difference is, if it's not in my confidence interval, I should be rejecting it, right? My confidence intervals tell me these are the only values the true difference could be. So anytime I assume a value outside of that confidence interval, I should be rejecting. If I've assumed it's a value within my confidence interval, well, then I should be failing to reject, right? So if I hit enter on 40 here, it'll update my p-value, it'll update my rejection decisions, and hopefully now I still am rejecting at every level. Sure enough, I am, right? Now, notice one thing didn't update, which is this shortcut T-dot test. So this is why I'm making you doing it both ways. Because I told you for this class, I'll only give you an assumed true difference of 0. But in practice, you might, the next step, if you take another stats class, or you get a job where they might want to do, I'll give you some examples here in a second, where you might want to use something other than 0, that T-dot test, you only use the assumed true difference of 0, right? So if you ever have a value that's assumed, your assumed true difference, anything other than 0, you actually have to break this down step by step. And, a lot of times we do just want to know, are male suicides greater than female suicide, or is that average difference above 0? But once I see that, like, it's huge, I might, can I say that the true difference is, on average, 40 more males commit suicide than females per county? I can here. I can reject that 40 or lower is that true difference, right? Another example, you know, more practically, like we might know things like, I don't know. I think the example I used last section, which is really dumb, but you know, I might be looking at like demographics for something, the use of something. So like maybe my product is Werther's Originals, and I want to know like what's the average age of you know, my consumers relative to the average age of regular candy consumers, right? I know that older people probably like these Werther's Originals. So I might want to say, is the age gap not just is it greater than 0, but is it by more than 20 years, right? I might have these assumed true differences that aren't 0 that I might be interested in. So if we ever want to do that, unfortunately, we can't use that shortcut. Now, Excel, I guess, you know, if you're out there in the job field working on this, someone should email them because it'd be very easy for them to code in. You could just tell it one more thing, right? You tell it the type of tails, you tell it what type of test, tell it what the assumed true difference is, right? But for whatever reason, that's not built in, okay? Any questions on anything up to this point? I want to do one more thing, and then I think we'll actually kind of get out of Excel here. So I just really want to hammer this point home. Let's say I then say, okay, I can reject that the difference is 40 or less. Can I reject that it's 42 or less? So if I looked at my confidence intervals here, okay, what levels of confidence should I be able to reject this assumed true difference of 42 at? Yeah, why? 42 is not in my confidence interval, right? You know, it's just below the lower bound for it 99. So it's not in my, I can't say it's one of the true differences. I should be rejecting. But at the 99, 42 is just inside of my confidence. So it could be the true difference. So I should be failing to reject. So hopefully if I hit enter here, my rejection decisions update here if I did it correctly to fail to reject. Okay. So just try to make that connection between my hypothesis testing and confidence intervals. Okay. Any other questions? So let's see here. What do I want to do here? I want to show you. So when we're doing these assumed true differences, so I had this one, let's say we did 40. Oh, I shouldn't have erased that. Sorry. Here we go. So I don't think I've mentioned this before or yet, but it's kind of something that I'm surprised someone hasn't interjected with a question about. So let's say I find some sample evidence that's like above 40, right? And it results in a test statistic, and I can clearly reject the null, right? So I can reject this value of 40. Well, I didn't assume it was equal to 40. I assumed it was less than or equal to, right? So why don't I do a hypothesis test for every single value in this range? Well, if the sample statistic I found was enough to be able to reject the assumed true difference of 40, well, let's say the assumed true difference was instead, I don't know, 35. Well, what would be true about the distribution is it would be centered around that. Well, now notice if I calculated something like a p-value, it's even smaller, right? So if I can reject 40, well, for sure, then I'm going to be able to reject any value below that. So that's why when we have these one-tailed tests, we only have to do the hypothesis test for that highest value in the range. Okay. There's questions on that. Okay. So this should be everything you need for that third Excel assignment, or that third Excel, the third question on the fourth Excel assignment, right? And you've got plenty of time to work, right? The next 2 weeks. So please reach out, come to office hours, reach out to me via email. I want you guys to all get as many points as possible as we get kind of towards the end here. I will, while I'm thinking of it right this second, save this and then just replace the file that's up on Canvas that says like in-class work or whatever. So I'll show you where this is at. So let's go to files, in-class data. I'll just replace this file so it has all the work we did today as well. Okay. All right, so we are then going to jump into, I put up some week 15 lecture slides. We're going to introduce the next topic, which is linear regression. This is what I think we're going to kind of get a little bit away, like especially for the first we'll eventually get back to hypothesis testing, but not gonna look anything as complicated or like what we were doing before. We're just gonna use some of the basic tenets of it. Linear regression, I think, is one of the most powerful and the most like interesting things of this class. We're gonna go away from computation. Like we're not gonna be doing as much kind of work with our calculators with linear regression as we are interpreting some output that Excel gives. So Excel is gonna be kind of our workhorse and do a lot of the computation, and then we're gonna use what it spits out at us and kind of interpret those statistics. Use those to make predictions. So we've got, going back a ways, we talked about correlation coefficients and covariance. So now we're going back to thinking about the relationship between two variables, x and y. As x goes up, what happens to y? Well, if x goes up and so y tends to go up as well, we say there's a positive relationship. If x goes up and y goes down, there's a negative relationship. If x goes up and y doesn't change, no relationship, right? So we kind of have these measures. Well, we can do hypothesis testing for any statistic. We could do, this is kind of weird. You can actually sort of do hypothesis testing for like variances and things like that. We're not going to tackle that, but you can, right? So here we could do hypothesis tests for the correlation coefficient and the covariance. We're actually going to be a little more precise. We're going to come up with something that's a better estimate even than the correlation coefficient. Okay. So anytime you have two variables, and this is going to be like a little bit of a review of things you probably saw in high school even. So let's say I've got variable x and variable y, right? I've got all these data points. So I just plot every single data point that I have. So maybe this is like years of education, income. And I go through this data set, person one, here's their years of education, here's their income level, plot that. Next person, here's their years of education, their income, plot that point, right? This is just creating a scatter plot. We talked about this like week 1 or 2, right? Well, what we're gonna do is then try to find a line that best fits our data. So if we had this scatter plot, and we're not gonna like do this by hand, there's gonna be a more technical way to do it. But the idea is, if I were to draw a line that best fit that data, like our line of best fit, you probably, I don't know, I feel like high school science, you talk about things like this, right? So you got this line that best fits the data. It's going to have some intercept value A, and it's going to have some slope B, right? Kind of slope representing the change in our Y variable from a change in our X variable. So what our slope B is really telling us, and here, I think in math, usually it's like y is equal to mx plus b. We're just writing it slightly differently, like a plus b times x. Your intercept value kind of tells you where that line of best fit starts. And then that slope value b is saying, okay, look, if x goes up by 1 unit, your slope b is telling you how much your y value is going up by. Now, if it's a positive, so if it's a negative slope, it's telling you how much it goes down by. All right. Here, your slope value is telling you if x goes up by 1 unit, how much was your predicted y value going up by? Think about it this way. If I had some actual numbers here, let's say a was 10, b was 5. And I said, okay, if x was equal to 1, plug a 1 in here, 1 times 5 plus 10, y would be 15. My slope should tell me that if x goes up by 1 unit, so 2 instead of 1, now what is my predicted y value? 2 times 5 plus 10. Sure enough, oh yeah, y went up to 20 or went up by 5. Okay? So that slope of that line is telling me that if x went up by 1 unit, how much would I expect that y variable to increase by? Okay. Is this like hopefully sound familiar? Like you've seen this in some math classes or something like this, right? We're just thinking about the slope here. Pretty basic. Now some terms that we'll need kind of moving forward, it'll start to think about our dependent and our independent variables. So we'll say that the y variable is our dependent variable and x is our independent variable, right? X is what's independently changing, and as a result, y is a function of that. So as x changes, y will change as well. So y depends on x. So a lot of times I'll use this term like our left-hand side, our y, or our dependent variable. Our right-hand side, our x, or our independent variable. All those are kind of referencing the same thing. Okay? We're then going to use regression analysis, which is just this tool, essentially, to figure out what that relationship is between our X and Y variable. Excuse me. What is that intercept and that slope that would give us that line of best fit? That's what regression analysis is going to do. Okay. So with that in mind, talk about, I could have, instead of a positive relationship like I had drawn up on the board, I could have some data where the line of best fit is going downward. Here, my value for B would be what? What can I say about my slope here? It would be negative, right? As X goes up, the predicted Y value, or where I'm at in this line, is lower, right? It's going down. So if I have a negative relationship, my slope is, or sorry, if I have a downward sloping line of best fit, I have a negative slope or a negative relationship. What if it was no relationship? What's my slope here?
0.
Yeah, right. As X changes, Y is not changing at all. So basically 0. If it's a perfectly perfect no relationship. And then we already talked about a positive relationship. Now, all of these I was also throwing the word linear on. So I'm not going to expect you to do this on the exam, but I will likely show you some examples next week. So kind of my idea, the roadmap is going to be, we talk about the linear regression stuff this week that I want you to know. Monday, we might have to finish it up a little bit, but I'll probably next Monday start to show you. And then also on Wednesday, things that I might not completely expect you to know. We'll still be kind of like talking about things that I do expect to know, but I'll kind of push the envelope a little bit, showing you like, what's the capabilities of this regression, right? It's going to go even further than what we're going to talk about in this class. And so I'm only ever going to give you examples or expect you to know things about linear relationships, like a one line of best fit here, a kind of nice straight line. But sometimes we have data that looks like this, where my line of best fit would need to be curved. And we'll kind of talk about some examples of that and show like we can actually pick up these concave and convex relationships in Excel and with linear regression as well. But we'll start out with linear. I'm just kind of mentioning this now that, there are some, more capabilities than what we'll originally start talking about. So how do I come up with this line of best fit, right? How do I figure out what this slope should be, what this estimated relationship is between my X and Y variable? Well, if I think about the actual Y values I'm looking at, so here's an actual Y value. If I were to plug this X value in to my line of best fit equation, I'm going to come up with some predicted Y value. So that predicted Y value we'll call Y hat, right? I'm only coming up with that based off of my intercept and my slope. The actual Y value is going to be that prediction, but there's also going to be some error term, or what we call epsilon, right? So any one of these, right? You can imagine here, I plugged in this X value. Well, my actual and my predicted Y here, well, I'm off by an epsilon there, but that's positive, right? So I'm making errors. Like this line of best fit, it's not perfect fit, right? It's the best fit. So for any of these observations, I'm going to be off a little bit. How much I'm off is this error term epsilon. So you can kind of rewrite this and think about my predicted Y is just what I'm coming up with, that A and B value. So the actual Y is that prediction plus some error. Now we don't know what this error is. So if I'm thinking about like years of education income, I can estimate that relationship on average across everybody, but the epsilon for Bill Gates is going to be huge, right? The epsilon for, the epsilon for, I don't know, someone who, I don't know, was a failed CEO and then dropped out of the workforce now makes it going to be huge, right? But on average, it'll give me this line of best fit. But for any one observation, I might have a huge error term. Right? So what we're going to be interested in, and I kind of already have this drawn up here on the board, right? We're making errors for all of these, right? Every single observation, our prediction is not going to be perfect. It's going to be off a little bit. But what we're going to try to do is we're going to try to minimize those errors. So if I looked at my actual Y values and I subtracted my predicted Y values, I want to minimize those errors. Now I'm making an error for every single observation. So I want to minimize the sum of the errors I'm making for every single observation. And then from there, I don't care what direction my errors are. I don't care if I'm like, my prediction's too low or too high, I just care that it's wrong. So we're going to square that error. Right, so that way it doesn't matter if it's positive or negative, it now becomes a positive value. And also squaring that error, just like with the variance, when you squared how far away we were from the mean, it's gonna really over penalize bad errors. Right, so this was the idea, if I was 1 away, 1 squared is still 1. If I was 2 away, 2 squared is now 4, right? So we're gonna minimize the errors that we're making squared. That way we don't care what direction we're making the error, we're over penalizing the errors across every single observation. So how many of you guys took like a calculus? Yeah, okay. So we're not gonna make you do calculus again, but I might reference some things just to kind of give you, if you have some reference. So how can I maximize an equation or minimize an equation? Well, I'm writing this out where my prediction is based off of my slope and my intercept. I want to choose the two values for the slope and intercept that give me this line of best fit or that minimize the sum of those squared errors. So if I want to minimize this equation, I take a derivative in respect to the two things I'm choosing. I then have two equations, two unknowns, set them equal to 0, solve for that. Next class, we'll kind of pick up on this and say, okay, look, if I were to have these two equations, two unknown, I could do the math, come up with some function that would give me these values for A and B. I'll mention a little bit how you would do this by hand. We are not going to do it by hand, because you can imagine if I had 1,000 observations, I'm like, how do you do this? There's easy ways we could do it in Excel, but it's not going to be fun, right? So we'll look at like what the end equations are, but then we'll say, okay, look, let's use Excel to be our tool. It'll do this regression for us. It'll spit out at us what those A and B values are. Now, what those A and B values are still going to be estimates. So just like we had the population mean, and we found a sample mean, there's going to be some true slope. We're going to be finding an estimated slope, right? It's based off of our sample data. Those X and Y values are coming from actual sample data, right? Or those error terms, okay? So before you guys get out of here, we're attending, try to give some incentives for people to show up, although they look like they're not necessarily binding for everybody. Whatever letter you want to respond with, gonna get 10 out of 10. So just make sure you get an answer on your way out. And I will see you guys on Wednesday. If you have any questions, once again, my office hours 2 to 4 today, Wednesday and Thursday. You mentioned you got in the new so I can't drop them until the due dates pass for all of them, right? So it'll be that week. I meant like drop like the not like drop release the new. Oh yeah, I'll put the 5th Excel and 5th connect up after second. Yep. Yeah, I didn't want to like throw them up there. We hadn't covered any of the material yet, so it didn't even make sense yet. Email. I didn't see it, but Friday I was in the ER like Thursday afternoon, all the way up to 80. Oh, shoot. I was at the gym. I just had to go back. Oh yeah. Oh yeah. I did see it. So I don't respond. I'm sorry. No, I can't remember if I did either. I don't think I did on Friday. Let's go there. All right. If I did, I have your link, so I have it long, so I'll if I did, I'll go back in and change it. I feel better.
They just had me on pain about muscle relaxers stuff, and then like they want to give me a CT scan, but they called me this morning and said they can't even get me in for another month. I was like, well, I'm gonna be gone by then.
Yeah. I hope you're feeling better.
So I'm doing this. I wrote down kind of like
Is this number 6?
Yeah.
So I think I put up on, this is the one I think, but I don't want to tell you this before I think this is the one I said you guys don't have to worry about.
Don't have to.
Yeah, so I put an announcement up and I mentioned in class, yeah, connect assignment question 6, right?
Yeah.
Something's wrong with it, so I think I know what's wrong with it, so it never references it anywhere. I think what it wants, it wants it in terms of percentages. So if you find like 0.05, it wants you to put 5, but it never indicates that anywhere. And so I just said,
Okay.
Yeah.
I was working on it for too long.
Yeah, sorry. Yeah. I put an announcement up there. Yeah, this one right here. So don't have to worry about it. Once the due date's passed, I'll go back in and just give everybody full credit for that one.
Alright, thank you.
You see what the commanders are being sold for?
6 billion, wasn't it? It's pretty wild.
After that, I was like, let me go. Like annual evaluations of what teams' values are. And so I was looking at the Browns.